Hello children. Today in the lesson Magnetic Effect of Current, we will discuss with torque on a current loop in magnetic field. We will use the concept of torque to study principle, construction and working of moving coil galvanometer. We will also see how we can convert a galvanometer into an ammeter and voltmeter. We will derive the expression for magnetic dipole moment of an electron revolving around the nucleus and solve some numericals based on these concepts. Let us see how to find out torque on a current loop in magnetic field. We know that a current carrying conductor in magnetic field experiences a force. If we take a current loop and it is placed in magnetic field, we will see that it will experience a torque and net force on this loop will be 0. This behavior of current loop is analogous to the electric dipole in uniform electric field. Let us consider a loop PQRS carrying a current I and a magnetic field is applied parallel to the plane of the loop. The arm PQ of the loop will experience a force, and according to Fleming's left hand rule, this force will be in the outward direction. Similarly, RS will also experience a force, and again according to Fleming's left hand rule, this force will be acting in the normally inward direction. So, the forces on PQ and RS are equal and opposite. Same current is flowing through the two parts. The magnetic field is same and hence the force will also be same, but the direction is opposite to each other. On the other hand, force on PS will be 0 because the current is opposite to magnetic field, and on QR also the force is 0 because current is parallel to magnetic field. So, PS and QR will not experience any force. Hence, we can say the net force on the loop is 0. But the forces on PQ and RS being equal and opposite, separated by some distance, hence they will form a couple. Okay, and they will rotate the loop in the magnetic field. We now take the case where the current loop PQRS is placed such that it makes an angle theta with the direction of magnetic field. The angle between the plane of the loop and magnetic field is theta. If we draw normal to the plane of the loop, let it make an angle phi with the direction of magnetic field. Force on PQ and RS are equal and opposite, separated by a perpendicular distance Pn. These two forces will provide turning effect to the loop. Let the breadth of the loop be B and the length be L. The section of the loop as seen from the top will be PS, making an angle theta with field, and normal to PS makes an angle phi with the direction of magnetic field. We will derive expression for torque in terms of theta and then in terms of phi. So first let us take in terms of the angle theta. Torque is product of force and perpendicular distance. So perpendicular distance Pn can be found out by using a right triangle PNS. In this triangle, cos theta will be Pn upon B, and hence Pn can be written as B cos theta. We also know that force on a current carrying conductor is ILB. L is length, I is current through the loop, through the conductor, and B is magnetic field. Length into breadth of the loop can be replaced by area, and hence we get torque as IAB cos theta. For n turns of the loop, torque can be written as NIAB cos theta. Now to derive the expression for torque in terms of the angle phi, we again start with torque is force into perpendicular distance. But now from the triangle PNS, if we take the angle S, that is angle PSN will be phi, and sine phi will be equals to Pn upon B, and hence now Pn will be written as B sine phi. So torque will be ILB into B sine phi, and this expression could be simplified to IAB sine phi. For n turns, we can write torque as NIAB sine phi. We know torque is a vector quantity. To write torque in vector form, we start with the equation torque is NIAB sine phi into a unit vector n in the direction of torque. We can now compare this equation with torque on an electric dipole in electric field. We know it is given by PE sine theta. If we take the angle as theta, then torque is PE sine theta. Hence, in this equation, we can write NIA. This term NIA is having same significance as dipole moment P in electrostatics. So NIA will be the magnetic moment. If we write NIA as M, then MB sine phi can be written as M cross B. That means if you consider a current loop, it behaves as a dipole. So you can see in the figure, current is flowing in the anticlockwise direction, and the arrowhead represents the direction of magnetic moment vector. So magnetic moment vector will be in a direction perpendicular to the plane of the loop. Okay. We can again use right hand thumb rule to write the direction of magnetic moment. So stretch the thumb perpendicular to the curl of the fingers. If the curl of the fingers represent current, then thumb points in the direction of magnetic moment. So what is magnetic moment? It is NIA. Hence its SI unit will be ampere meter square. Current is measured in ampere and area in meter square. Also, we can use the above expression to write the values of maximum and minimum torque. If phi is 0, then torque will be 0. Whereas if phi is 90, then torque will be maximum and the maximum value will be NIAB. The above formula for torque can be used for any loop irrespective of its shape. Whatever be the shape of the loop, the formula for torque will be M cross B or MB sine phi, where M is the magnetic moment. We take a numerical based on torque. It is question of the NCERT textbook number 13, 4.13. A circular coil of 30 turns and radius 8 cm carrying a current of 6 ampere is suspended vertically in a uniform horizontal magnetic field of magnitude 1 Tesla. The field lines make an angle of 60 degree with the normal to the coil. Calculate the magnitude of counter torque that must be applied to prevent the coil from turning. Would your answer change if the coil in A were replaced by a planar coil of some irregular shape that encloses the same area? So we know whenever current is passed through a loop, a torque will be acting. this will deflect the coil. This will deflect the loop. So we need to apply a counter torque which will be equals to the torque produced so that we prevent the coil from turning. So torque will be NIAB sin phi. We are using sin phi because magnetic field makes an angle of 60 degree with the normal to the plane of the coil. That is why we are using the formula NIAB sin phi. Now N, I, B and phi are given. We can find out area using the formula pi r square and substitute the values in the formula. Torque is NIAB sin phi and the result is torque is 3.1 Newton meter. Okay. For the B part, the answer will not change because torque depends upon area, but it does not depend upon the shape of the loop. It depends upon the area of the loop, and hence the answer will not change if the loop is replaced by another loop that encloses the same area, though its shape may be different. Okay. Next we come to moving coil galvanometer. Galvanometer is a device used to detect the presence of current in the circuit. We have used galvanometer in the experiments of meter bridge and potentiometer to detect whether the current is flowing through the circuit or not. It works on the principle that a current loop in magnetic field experiences a torque. Let us see the construction. This is the figure given in the textbook, but it is not so clear. We can take a three-dimensional view of the galvanometer. It basically consists of a coil with many turns free to rotate about a fixed axis in uniform radial magnetic field. The concept of radial field I will just explain what it is. But basically what it consists of, a coil of many turns which is free to rotate about a fixed axis in the magnetic field. The ends of the coil are connected to springs. We can see two springs, one at the front and the other at the back. So these springs, they control the rotation of the coil in magnetic field. And very important, a soft iron core. We can see a cylindrical soft iron core which makes the field radial, and it also increases the strength of the magnetic field. Okay, the permeability of soft iron is very high. So field lines will penetrate through the material and hence increase the strength of the field passing through the coil. Okay. Radial magnetic field is very important in the working of moving coil galvanometer. The radial magnetic field is applied in a moving coil galvanometer to produce a constant torque on the coil. That is, to produce a torque that does not depend upon the angle between the plane of the coil and the direction of magnetic field. We know that if phi is the angle between normal to the coil and magnetic field, then torque is equals to NIAB sin phi. And torque will be NIAB if phi is 90, because we know sin 90 is 1. So if we want torque to be independent of the angle phi, then plane of the coil should always be parallel to magnetic field. Okay, plane of the coil should always be parallel to magnetic field for all orientation of the coil in the field. And how is this made possible? Radial magnetic field can be achieved by making the pole pieces cylindrically concave, concentric with the axis of the coil, and by winding the coil on the soft iron core. So making the pole pieces concave and use of soft iron core will make the field radial. Okay. Working of moving coil galvanometer. When current is passed through the coil, a torque is produced. This torque is given by NIAB sin phi. For radial magnetic field, phi is 90. Hence, sin 90 will be 1. Therefore, torque will be equals to NIAB. This torque is called magnetic torque, which rotates the coil in magnetic field. The counter torque is provided by the spring, which balances the magnetic torque. The counter torque is given by K phi, where phi is the deflection in the galvanometer and K is the torsional constant of the spring. It is the restoring torque per unit twist. From equation 1 and 2, K phi is equals to NIAB. Hence, phi can be written as NAB upon K into I. Okay. This equation shows that the deflection in the galvanometer is proportional to current. Greater the current flowing through the galvanometer, more will be the deflection indicated by the pointer. So we know that phi is NAB upon K into I. This formula is very important. Now we define current sensitivity of galvanometer. It is deflection of galvanometer per unit current. A galvanometer will be highly sensitive when small current flowing through it can be detected by the galvanometer. Means the deflection can be shown by the galvanometer. So it is deflection for unit current flowing through the galvanometer. So deflection per unit current will be equals to NAB upon K. Hence, we can increase the sensitivity of the galvanometer by increasing magnetic field, that is using strong pole pieces and using a soft iron core. It can also be increased by using a material which has smaller value of K for making the spring. The torsional constant K should be small, the sensitivity will be more. It can also be increased by increasing N, that is number of turns of the coil, and A, that is area of the coil. Next we define voltage sensitivity. Voltage sensitivity is defined as deflection in the galvanometer per unit voltage. To write the expression for voltage sensitivity, we divide current sensitivity by R. So deflection per unit voltage will be nothing but deflection per unit I into R, where R is the resistance of the galvanometer. So this will be equals to NAB upon KR. And just as current sensitivity, voltage sensitivity can also be increased by increasing magnetic field, that is using strong pole pieces and a soft iron core. It can be increased by decreasing the value of K using a spring which is made of material which has smaller value of K, and by increasing number of turns and area of the coil. But important to note here is, on increasing N, the resistance of coil also increases, hence voltage sensitivity may not increase. So increasing current sensitivity may not necessarily increase the voltage sensitivity also, because on increasing N and A also, what will happen? The resistance of the coil will increase and hence the voltage sensitivity may not increase. Okay. Galvanometer can be used both as an ammeter and as a voltmeter. First we will see how to convert a galvanometer into an ammeter. A galvanometer is a device with moderate resistance and ammeter has very low resistance. Moreover, resistance of ideal ammeter is 0. So to convert a galvanometer into an ammeter, we connect a very small resistance parallel to the coil of galvanometer. because by parallel combination resistance decreases. So we connect a very small resistance S parallel to the coil of the galvanometer. So if I is the current to be measured using ammeter, let us assume Ig is the maximum current that can flow through galvanometer. So remaining current, that is I minus Ig, will flow through the shunt resistance. In parallel combination, potential across galvanometer will be same as the potential across the shunt. So potential difference across galvanometer is Ig into G, and across shunt the potential difference is I minus Ig into S. Therefore, S can be written as Ig into G upon I minus Ig. So thus we can convert a galvanometer into a ammeter. We take a numerical on conversion of galvanometer into ammeter. NCERT question number 28. A galvanometer has a resistance of 15 ohms and the meter shows full scale deflection for a current of 4 milliampere. How will you convert the meter into an ammeter of range 0 to 6 ampere? We know to convert a galvanometer into ammeter, we require a shunt in parallel. And potential drop across galvanometer is same as potential drop across shunt. Given Ig is 4 milliampere, resistance of galvanometer is 15 ohm, and the current to be measured is 6 ampere. When we substitute in above equation, we get the result as 0.01 ohm. Hence, a resistance of 0.01 ohm is to be connected in parallel to the coil of galvanometer. Here is another numerical. In the circuit, the current is to be measured. What is the value of current if the ammeter shown is a galvanometer of resistance 60 ohm? Is a galvanometer described in A but converted into an ammeter by using a shunt of 0.02 ohm? Is an ideal ammeter with zero resistance. So in the three cases we want to find out what is the current in the circuit. In the first case, if you take that ammeter is a galvanometer of resistance 60 ohm, the total resistance of the circuit will be 60 plus 3, that is 63 ohm. We know current is V by R. Hence, I will be equals to 3 by 63, which is nearly 0.048 ampere. Now the second case. We have a galvanometer that is converted into an ammeter using a shunt. So the resistance in the circuit will be Rs into Rg upon Rg plus Rs. Taking Rg as 60 and Rs as 0.02, we get the equivalent resistance as 0.02 ohm. To find the current, we need total resistance. Total resistance of the circuit is 3 plus 0.02, that is 3.02 ohm. And hence now the current will be 3 upon 3.02, that is 0.99 ampere. Okay. And in the third case, I already told you ideal ammeter has zero resistance. So if the resistance of ammeter is 0, the current in the circuit will be 3 by 3, that is 1 ampere. Okay. So an ideal ammeter will give us the correct value of current. Whereas if we convert galvanometer into an ammeter, the current is nearly equals to that in the case of ideal ammeter. And if we are using galvanometer to measure current, the current will turn out to be very small. Okay. So ideal ammeter always has zero resistance. And to convert a galvanometer into an ammeter, we need to decrease its resistance by connecting a shunt resistance in parallel with it. A small resistance is connected in parallel with the galvanometer. Now let us see how to convert a galvanometer into a voltmeter. Galvanometer is a device with moderate resistance, but resistance of voltmeter is very high. For an ideal voltmeter, the resistance is infinite. So to convert a galvanometer into a voltmeter, we connect a high resistance in series with the galvanometer so that the resistance increases. So we need to connect a high resistance in series with the galvanometer. How to find this resistance? We know V is equals to IR. So potential difference across the given load resistance is the sum of potential difference across galvanometer and across the high resistance. So total potential V will be equals to Ig within brackets G plus R. Hence we can write the resistance required to convert the galvanometer into voltmeter R as V upon Ig minus G. Okay. So using this formula we can calculate the resistance required to convert the galvanometer into voltmeter. Okay. We take a numerical based on conversion of galvanometer into voltmeter. A galvanometer has a resistance of 12 ohm and a meter shows a full scale deflection for a current of 3 milliampere. How will you convert the meter into a voltmeter of range 0 to 18 volts? So we need to connect a high resistance in series. Okay. So the resistance required is given by V upon Ig minus G. We are given resistance of galvanometer is 12 ohm. Current through galvanometer is 3 milliampere and potential to be measured is 18 volts. When we substitute in above equation, the resistance R required is 5988 ohm. That means we need to connect a resistance 5988 ohms in series with galvanometer to convert it into voltmeter so as to read 18 volts. Okay. We take another question for conversion of galvanometer into a voltmeter. This is a NCERT exemplar question. A multi-range voltmeter can be constructed by using a galvanometer circuit as shown in the figure. We want to construct a voltmeter that can measure 2, 20 and 200 volt using a galvanometer of resistance 10 ohm that produces maximum deflection for a current of 1 milliampere. Find R1, R2 and R3 that have to be used. Given is current through galvanometer is 1 milliampere and resistance of galvanometer is 10 ohm. First let us convert the galvanometer into a voltmeter of range 2 volts. We know that V is equals to IR. So 2 is equals to Ig within brackets G plus R1. Similarly, for 20 volts, the equation will be Ig within bracket G plus R1 plus R2 is equals to 20. And in the third case for 200 volts, we will have Ig within bracket G plus R1 plus R2 plus R3 is equals to 200 volts. Okay. In the first equation, when we substitute the value of Ig and G, the result is R1 is equals to 2000 minus 10, that is 1990 ohms. So substituting value of Ig and G in equation 1, we get the value of R1. Now we can substitute the value of Ig, G and R1 in equation 2. The result will be R2 is equals to 18 kilo ohms. And similarly from equation 3, we will get R3 is equals to 180 kilo ohms. So thus we can convert the given galvanometer into a multi-range voltmeter. Okay. We come to the last topic of this lesson now, the magnetic dipole moment of a revolving electron. We know that in an atom, electron revolves around the nucleus, and this revolving electron constitutes current. The electron moving around the nucleus constitutes current. We know current is charge per unit time, charge that is flowing per unit time. Hence, we can write I as E by T. And the direction of current will be opposite to the direction of motion of electron. So, let us assume electrons are moving with a velocity v in a circular orbit of radius r. So, time required to complete one rotation, that is capital T, will be 2 pi r upon v. When we substitute this value of time in the expression for current, current will be EV upon 2 pi r. And this current will produce magnetic moment. In case of electron, we represent magnetic moment by vector mu. And this vector will point normally downwards, given by I into A. The magnetic moment vector mu will be I into A. We know current is EV upon 2 pi r. Area of the loop is pi r square, and hence mu can be written as EV r upon 2. So this is magnetic moment associated with electron moving with a velocity v in a circular orbit of radius r. This equation we multiply and divide by mass of the electron. So the result will be mu is equals to E upon 2me into MEVR. Me is mass of the electron. MEV is the linear momentum and R is the perpendicular distance of electron from the axis of rotation. So momentum into perpendicular distance from the axis of rotation is angular momentum. Okay, angular momentum vector is normally pointing normally upwards. So the result is mu is equals to E upon 2me into the angular momentum vector L. From this equation, we find out magnetic moment per unit angular momentum, and it is equals to E upon 2me, which is a constant known as gyromagnetic ratio. Okay, E upon 2me. E is charge on the electron, me is mass of electron. These are universal constants. Okay, we can also simplify it further. We know that mu is equals to E upon 2me into L. Now, according to Bohr's postulates, Bohr's atomic model, the second postulate states that for an electron revolving around the nucleus, only those orbits are possible for which angular momentum is integral multiple of h upon 2 pi. We have replaced L by nh upon 2 pi, where n is the principal quantum number. For first orbits, its value is 1, for second 2, and so on. Okay. So in this expression, if we take n as 1, we get the result mu is equals to EH upon 4 pi me. We know in hydrogen atom there is only one orbit and only one electron is present. So if we find out the magnetic moment for electron in the hydrogen atom, n will be equals to 1, and the result is EH upon 4 pi me. And this constant is known as Bohr magnetron. Okay, so we have derived expression for magnetic dipole moment of an electron revolving around the nucleus.